Welcome to a code report solution video. In this video, we're going to be going over the solution to problem 2 from Topcoder SRM 733 entitled Building Spanning Trees Div 2. The problem states, consider an undirected complete simple graph G on n vertices. The vertices of G are labeled from 1 to n. Specifically, each pair of distinct vertices is connected by a single undirected edge, so there are precisely n times n minus 1 divided by 2 edges in this graph. You are given a set E that consists of n minus 3 edges of this graph G. More precisely, you are given the x and y with n minus 3 elements each. For each valid I, xi, yi is one of the edges in E. A spanning tree of G is a subset of exactly n minus 1 edges of G such that the edges connect all n vertices. You may note that the edges of a spanning tree do indeed form a tree that is a subgraph of G and spans all its vertices. We are interested in spanning trees that contain all of the edges in the provided set E. Compute and return the number of such spanning trees modulo 987,654,323. Two spanning trees are different if there is an edge of G that is in one of them but not in the other. And note that n, the number of vertices, will be between 4 and 1000. Each element in x will be between 1 and n minus 1, and each element in y will be between 2 and n. And for each valid I, xi will be less than yi, and all edges in E will be distinct. So let's take a look at some of the terms, undirected, complete, simple, and spanning tree, and define these for those that aren't too familiar with graph theory. So an undirected graph is a graph in which edges have no orientation. So I've taken this diagram from Wikipedia, and it simply shows that the graph on the left is a directed graph and the graph on the right is an undirected graph. So here you can only traverse between this point to this point in this direction, from this point to this point in this direction, and between these 2 points you can go either way. But here you can go anywhere you want. There's no orientation in this graph. A complete graph is a graph that contains all possible edges. So once again, another diagram taken from Wikipedia. This graph has 5 vertices, and you can see that from every vertex you can get to any other vertex. So that's what a complete graph is. And last but not least, a simple graph is an undirected, unweighted graph with no multiple edges or no multiple loops. So technically, stating that this is an undirected, complete, simple graph, the undirected is redundant, but it's okay because it's just making it a little bit more explicitly clear. So here we have a diagram showing 3 graphs. So the first one is a simple graph because it's undirected, there's no orientation, there's no weights on any of the edges, and there's no multiple edges or no loops. So in the second graph here, you can see that there are multiple edges. Another term for this is parallel edges, basically meaning you have the same edge from point A to point B more than once. And in our third graph here, you can see that this is a non-simple graph because it has loops. So we're told that the graph that we're given is undirected, complete, and simple. So the next term to deal with is spanning tree. So this is taken directly from the problem. So they define what a spanning tree is in the problem, which is nice. And it says a spanning tree of G is a subset of exactly n minus 1 edges of G such that the edges connect all n vertices. So n is the number of vertices in our graph. And a spanning tree consists of a graph with n minus 1 edges, and it connects those edges connect all of the vertices. So this is a graphic taken from tutorials point, and it shows you that you have your graph G here with n equals 3, so 3 vertices A, B, and C, and there are 3 possible spanning trees. So you can see that each of these graphs or subgraphs, which are spanning trees, have n minus 1, so n is 3, meaning n minus 1 is 2, so we have 2 edges. And so these are the different orientations that we can use to connect all 3 of our vertices with those 2 edges. So now that we have defined these terms, let's take a look at an example and what this problem is asking. So here's our example. N is equal to 4. The number of vertices is equal to 4. And our x and y, x is equal to 1 and y is equal to 2. So remember that the problem said that the edges in our E are going to be equal to n minus 3. So n is equal to 4. So that means we should only have one edge. So this edge is represented by vertex 1 and vertex 2 being connected. So this is what our graph looks like. We've got 3 and 4 off by themselves, and 1 and 2 are connected. And so the question is asking what are the possible spanning trees that we can create from this initial set, this initial graph E. And so one example could be this. So connecting node or a vertex 3 to vertex 1 and connecting vertex 4 to vertex 2. So note that in our definition of spanning tree that we were given, it says that a spanning tree has n minus 1 edges in it. And remember that we're given our graph E that has n minus 3 edges in it. So we know that we're going to be adding 2 edges in order to get our spanning tree. And so the question is basically asking, what are the different ways that we can add these 2 edges in order to get a spanning tree? So this is one of them. This is the second one, third, fourth, fifth, sixth, seventh, and eighth. So what you'll note from all of these spanning trees is that they are minimally connected and maximally acyclic. So acyclic meaning that there are no cycles. So if we were to add a edge here, we would have a cycle, and that would no longer define this as a spanning tree. And so that's basically the whole problem. Conceptually, it's pretty easy. So how are we going to solve this? So really, this is less of a graph theory problem and more of an algorithm problem, and we can use an algorithm called quick union in order to solve this. So if we go back to our original graph, what we're going to use is this quick union algorithm. I'm not going to cover that algorithm. There's a really good video done by Princeton that's only 7.5 minutes long. I'll link it up here. But using that, we can figure out how many connected components there are and what the size of those connected components are. And so basically what we want to find is we want there to be 3 connected components, because we know if we have 2 edges to connect these connected components, then we want there to be 3 connected components. If we have a 4th one, we don't have enough edges. Those 2 edges that are given to fill in are not going to be enough to connect all of the components together. And if we only have 2 components or 1 component, adding those 2 extra edges we're going to end up with cycles for sure. So we're going to use quick union to figure out how many components there are, and once if there's 3, we're going to continue on. If there's not 3, we're just going to return 0 because there's no possible spanning trees from that graph E. And then we're going to figure out, quick union will also give us the number of vertices in each of our components. So our first component has 2 and our other 2 have 1. And so once we have these numbers, we're just going to use that to generate the number of possible spanning trees. So we know we have 2 edges, so we have 3 possible choices for our edges. We have A, we have B, and we have C. So we need to choose 2 of these 3 possible edges to connect our components to end up with a spanning tree. And so basically, of these 3, we can either choose A and B, A and C, or B and C. So the total of these 3 choices of edges is going to give us our answer, choosing A and B plus choosing B and C plus choosing A and C. So the last thing to do is just to calculate each of the values of A, B, and C. So A is going to represent the number of different positions or ways that we can connect this component and this component. And this is simply going to be equal to the number of vertices in each component multiplied by each other. So A will be equal to 2 times 1, and that just represents that we can either connect 3 to 1 or 3 to 2. And for B, it's also going to be 2 times 1, and for C, there's only one way, so 1 times 1. So that gives us our values of the different number of ways that we can use edge A to connect these 2 components. So A is equal to 2, B is equal to 2, and C is equal to 1. And then once we have these, we just plug them into this formula, and we have our answer. So we're going to end up with 4 plus 2 plus 2 is equal to 8. And so that gives us our solution. So there's a lot of graph theory sort of words and terms you need to know in order to set yourself up for finding the solution. But once you have it, it's really just using quick union to find the number of components. If they're equal to 3, we can then go on to calculate the values of A, B, and C, and then just plug them into this formula. So let's take a look at our code. So here's our function, get number of spanning trees. It takes 3 parameters, an integer n, the number of vertices, and 2 vectors, x and y, which represent the edges in our subgraph of GE. So the first thing we do is we are going to declare m equal to n minus 3, and this is just equal to the size of x and y. And the next thing we're going to do is we're going to make x and y 0 index. So initially they're given to us with the values 1 to n, but it's easier to work with 0 to n minus 1. And then we have 2 vectors that we're declaring, rt for root and sz for size. So root is going to be initialized initially with just 0, but then we're going to fill it using this algorithm called iota. So you pass it first and last for range, and then an initial value 0. And then so the first element of root is going to be 0, the next one 1, the next one 2. So this is our initial value, and then it just increments every value after that by 1. And we're initializing size to have a value of 1. And so we pass both RT and SZ to our quick union algorithm with each edge, which we give xi and yi. So very quickly, if you've taken a look at that quick union video, this is the algorithm we can use. And basically what we're going to end up with afterwards is in our root, if the index of our root is equal to the value at that index, we know that that's sort of the root of one of our components. And the corresponding index in the size vector is going to represent the number of vertices in that component. So that will sort of inform the next line, which basically is going through, looping through 0 to n minus 1, and it's checking if the value at our index in root is equal to that index. Then we know we found the root of a component, and we want to push that into our vector component. So at the end, we're hoping that the number of elements in this vector component, or comp, which stands for component, is going to be equal to 3. And so we're pushing into it the size of that component, which we're going to use to calculate our A, B, and C. So the next thing we do is just check, is the size of our component vector equal to 3? If it's not, we're just going to return 0 because it's not possible to create a spanning tree. If it is, we're going to continue on, calculate our A, B, and C by multiplying the sizes of our different components. So you can see this is component 0 multiplied by component 1, 1 with 2 and 0 with 2. So this gives us A, B, and C. And then the last thing we do is just return this formula that which we showed in the visual algorithm, A times B plus B times C plus A times C. And then don't forget to do our modulus. And it's not defined here, it's defined outside the function, but it's just a const integer set to the value of the modulus given in the problem. And so the last thing to do is to talk about the time complexity. So the time complexity is going to be driven by the quick union. Everything else is linear. And it's a known fact that the complexity of the quick union algorithm is big O of n times alpha n, where alpha is the inverse Ackermann function. I'll leave a link to a discussion about this in the description.
As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.